So Kireeti, floor is yours.
I don't need it. And this works. So I want to talk about the self-driving network, and I want to talk about how we can realize this. Last time I gave a pitch on the vision, and now I want to sort of continue that. And one of the things that I did was to draw an analogy with the self-driving car. From vision to first, real prototype took 10 years. And in fact, when the vision happened, which was this grand challenge for a self-driving network in 2004, I think it was about 25 teams that took part. None of them could succeed. So the question that many people are asking me is, will the self-driving network work? Will it even succeed? And if so, will it take 10 years? So here's the journey for the self-driving car. In 2004, there was this DARPA grand challenge to build a self-driving, fully autonomous vehicle. And in 2014, you have this thing. So 10 years, right? Of course, there was the challenge in 2004. Like I said, nobody managed. But in 2005, there's a very simple thing, which was to drive on the freeway for 240 kilometers. They did it in 2005. But here you have a car with no steering wheel. So the question is, what do we do in the self-driving network? How do we get there? What are the steps that we can take? But the first is sort of a recap from last time. The self-driving network would accept guidance, accept, call it what you will, instructions from an operator at a very high level, and it will start doing everything else. So it'll self-discover the parts, it will configure itself, but it'll do much more than just configure. It'll actually monitor itself. It'll auto-detect when the new customers come on board and knows what services to give them the services, monitor and update service delivery as needed. It'll self-analyze, and finally, it will report what it's doing. And that's also a very important part. So basically, there are 5 technologies for self-driving. And this order is a little bit different from last time. There's telemetry. What is the network doing? There's multidimensional views. What we do today is, get a lot of telemetry and, store it in a file, put it on the disk, dig a deep hole, put the disk inside there, cover it up, leave it there. In case somebody asks tomorrow what happened, and then we start digging another hole, putting some more there. Is this not funny? No, I guess not. People don't use the telemetry that they get. So I want to do much more with it. Automation, declarative intent, and decision-making. So I'm going to start by recapping these different technologies. And for cars, you have the usual telemetry. Tell me how fast I'm going. Tell me how fast the engine is turning, especially if I have a manual transmission. I need to know when to change gears. Tell me how much gas if you have a petrol car, or how much battery I have if you have an electric car. Tire pressure sensor. But now we've added some more things. Radar, if you have this cruise control that automatically stops when there's a car in front of you slowing down. Sonar for parking assist. Cameras of all kinds, but these are really to help you drive better. But when you think about self-driving cars, either you get stereo cameras to get a depth perception, or you get this thing called LiDAR. And so we're really changing how we think about telemetry for cars when it comes to self-driving. So in networks, what can we do? You have the usual thing where you say, here's some SNMP MIBs, here's some different stuff. But what we're saying now is a much more sophisticated approach to telemetry. So we have, I'll just come out here and point. You have a query engine, and you have these applications. And these applications are going to tell the box what you want to measure. So we have these things called sensors. So you have a sensor on the line cards, and you have a sensor on the routing engine. where the control plane is running. And essentially, you're going to, once you make that sensor, you're going to get streaming data coming to the collector. And you can just put in a database, you can visualize it, you can do lots of things with it. The important thing here is, this is streaming real-time telemetry. And it's of many, many different kinds. It is optimized for use by a machine. And that's the direction we want to go. And of course, for a human to absorb it, you'll find different ways of visualizing this. But in the end, this is really so that I can get lots and lots of telemetry. I don't want to slow down getting this. I want this to come in real time. I don't want to keep asking, like how typically you do things with SNMP. There's seats up front, by the way, for people coming in. So this is a very different approach. And we've been working on this for over 3 years, and now you can see the fruit of this. It is really important that you understand that when I talk about the self-driving car, the journey has already started. We don't have a self-driving network. The journey has started. We don't have everything today, but we're putting these pieces in place. So this is the first piece. The second piece is this multidimensional views. You can call it multimodal. And in machine learning, what people are saying is, I have this device or this program that can hear what you're saying and tell me, interpret all that and do basically speech recognition. I have this other thing that can read what you're saying and tell me what's going on. So, for example, if you have a video, you can say, okay, there's some pictures happening, there's some speech happening, and there's subtitles happening. But the most effective way of doing this is I'm going to absorb all three. I'm going to look at the pictures, I'm going to hear the speech, and I'm going to look at the subtitles and really understand what's going on in a much deeper way. That's called multimodal learning. Well, what we do in networks is, and I was only half joking when I said, you take all this telemetry that you're getting, put it on a disk and bury it somewhere, and then you get some other one. You can come up front. So instead of having this siloed approach, I want to start correlating the stuff. So here we have, I know what my neighbor is doing, I know what my links are doing, I know what the exit point in my network is, but I want to correlate that. I have L0, L1 boxes, basically optical stuff. I've got middle boxes which pretty much disappear from when I'm monitoring my network because they try to pretend they're not there, but they're important. I have a global topology view, I have servers and applications, and I need to know how they're doing. But if I do all this in silos, I'm not going to really get anywhere. So I want to get to the point where you correlate this information across geographies, across layers of the network, across peers, across clouds, across in time. So you have time-based trending. And then you can start making decisions. You might make an optimal local decision based on a global state. Or you might take an S-flow thing that says, here's my source IP, here's my dest IP. Like, what does this mean? So you want to correlate the source IP with a DHCP, with radius, and say, this is this subscriber trying to talk to something, and look at the dest IP, look at the exit point of the network, look at the peer, and say, okay, this subscriber is talking to this peer, this is where the traffic is going. So suddenly, this S-flow information is just 4 bytes here and 4 bytes here. What does it mean? Makes a lot more sense. So if we start doing this correlation, we get much more out of our data. So just getting the telemetry and then putting in a disk and burying it in the ground is not helping us. Automation. It's obvious what automation you have in cars, but in the network, we have a lot of stuff going on. So what we have, if you look at this as the Juno stack, at the bottom here is the hardware. You have the chassis and you have the line cards. But coming up from there, you've got all these layers. And we are doing a lot of stuff in all these layers to really improve the way you can interact with the box. The most important thing is this, netconf. So you can talk to the box in this much higher level way. And now this is becoming a standard. You can have restconf as well. You can do a CLI. Deep dark secret is when you do CLI, you're actually doing netconf locally on the box over a Unix socket. Yes, I'm a geek, and I talk about such things. But it is not CLI the way you think of it. When you type at the CLI, it turns into a netconf call within the box. But above that, we have a PyEasy, basically based on Python, or a RubyEasy library. So you can start doing things on the box. And then we have infrastructure using Ansible, Salt, Puppet, Chef. So you can start automating a lot of things. So if you want to make changes on the box, if you want to remember how you want to snapshot what your config was and go on to the next thing, all of these things can be much, much easier. So we have put into place automation. Again, the main thing I want to tell you is we are in the journey. So look at this, build a highly automated network. It's not marketing, we're actually doing this. And it says here, build more than a network. What it's saying is, build a self-driving network. But we're not quite there yet. Declarative statement of intent. If you get into one of those Google cars, there is no steering wheel, there's no pedals. What can you do in there? Well, you can say where you want to go. You'll see a little dashboard, and you can enter where you want to go. So you might say, take me to the airport, and I don't know which airport that is, probably San Jose Airport because it's going 101 south. But you can say, that's where I want to go, and here are some hints. Take me in the fastest time, take me in the least distance, fewest tolls. We don't do too many tolls there. Most efficient use of battery, that's me with my very poor little car. It's a Leaf, doesn't have very big battery, so I need to be very concerned about how to get there. But in fact, what if you don't even have to talk to the car? The car talks to your phone, the phone says, hey, this guy's got an appointment at this time, it's in this place, and then says, okay, I'll just take you there. So we're looking at these things where we interact with the car at a much higher level than today, where I have to choose which gear I want to be in, which lane I want to be on, which freeway. I'm choosing all these things manually, where the system can just do it on its own. So if you look at the networks, we have declarative intent today. It's not, again, something that's coming in 5 years. If you look at down here, because I see Ankur, I'm going to talk about Contrail. You've got virtual networks. And you say, hey, I have this virtual network, I have this other virtual network. Here are the policies between these virtual networks. And when a VM comes up, I'll automatically say, oh, this VM should be in this virtual network. Here are the policies that I need to apply to that VM so it can talk to its friends and talk to some of its colleagues so that the right things happen. When the VM moves, you want the policies to move with it. All of this is automated. You don't talk at that down level. You talk up here saying, this is the high level way I want to do this. If you look at North Star, basically you define path constraints. This is the kind of, I don't know if they can see, but this is the bandwidth I need, this is the latency I need, this is the diversity requirements, and then it'll go off and instantiate those LSPs. But imagine that you could get to an even higher level. Imagine that you could say, here are the economic hints I'm going to tell you. These are the valued customers. These are not so valued customers. This is the valued applications. This is not so important applications. Because whenever you have finite resources, you need to know where you have to spend them. Here's my peers. I've got all these peers. These are the peers that I have to pay a lot of money for. Here's the peers I pay less money for. So essentially, you're giving economic hints to the system saying, I want you to optimize subject to these constraints. I want to give service hints as well. So this guy needs a lot of bandwidth. This other guy needs low latency. This other guy needs redundant connections, redundant services. This guy belongs to the multi-cloud environment. And so here's the ranking that this customer has for the clouds. Again, when I start trying to optimize, I need to know these things. I want to work at that level, and I don't want to work down here saying this is the BGP policy that I'm going to use, or these are metrics I'm going to put on my IGP costs. That's way too low level for what we should be doing. And so you define the services, and the system sets them up, and the system monitors them and continuously optimizes. The important thing here is when people think about self-driving networks, they talk about zero-touch provisioning. They talk about these things, and that's a component. But that's just the first part of it. You start off by configuring things the right way, but you need to continuously monitor it, optimize, re-optimize, move things around. And so a self-driving network is not just that first thing where you say, the network is up, the service is up, I'm done. It's a continuous process. To do that, well, let me first finish with this slide. The intent-based network basically says, say what you want to do, not how to do it. Today, we spend a lot of time saying how to do things. So you want to work at this level where you're at this high-level declarative statement, and essentially you have a service database, you have an analytics database, or actually it should be a telemetry database. And then you have this thing in the middle that does all the analytics and then says what you should do. And then you send the configuration down to the devices. So for example, in Contrail, the high-level statements will be about virtual networking requirements. And as you do that, the devices down here are the vRouters on servers. So it's not necessarily a physical device. In this case, it's actually servers with a vRouter on it. And as you bring up new VMs, they'll get placed on the right device, which is a server, and the right policies will be applied to it. As I said, Northstar also does this. Here, your abstract connectivity requirements are your high-level declarative statements. And the low-level things is compute a path and send it with PCE down to the devices. So in this case, the devices are typically core routers or maybe edge routers. But as I was saying, you're doing this continuous monitoring. And as you see situations, you have to make a decision. Just as the same as a self-driving car, you're sitting in this lane and you need to say, oh, wait, there's a traffic jam coming up. I want to change lanes. Or, you know, there's a blockage in the freeway. I need to get off and get onto a different freeway. So these are all decisions that you make. Sometimes local decisions, sometimes global decisions. How do you make these decisions? Well, you can have a rule-based system that says, if this, then that. You know, when you see a situation, do something. And it's very, very simple, except the number of rules you need gets really, really large. So individually, the rules are simple. It's very straightforward. But very, very quickly, it becomes unmanageable. So machine learning is actually a very, very cool thing here. You just give it lots of examples of something, and it will start learning. Now, I have a daughter who just got her license about a month ago. She did maybe 50 hours of driving. She has a license. She's actually not bad. I don't say it because she's my daughter. I keep telling her that she has to be really, really careful. But she's not bad. The Google car has had several million miles of driving. Still not there. So machine learning is really slow, but it gets there. The programming-based stuff, the rule-based stuff, doesn't get there very quickly. So I think machine learning is something really cool. I think we should be applying machine learning more in networking. I know that every other field of endeavor is using machine learning. So drug discovery, radiology, financial markets, of course, the self-driving cars, all of these guys are using machine learning. I think we're a little bit behind. So we need to do this. Is this 5 years away? Actually not. We just Juniper bought a company called AppFormix in December, mid-December. And what they do is a bunch of really cool stuff. I think Ankur will tell you more. But at the heart of what they do is machine learning. So this is the first application of machine learning more to servers than to networking, but they're doing a pivot and saying, okay, we have the technology, let's put to use in networking. So here's the first step, but we need to do more. Okay, so where do we take this? Like I said, my main message to you guys is, this is not a 10-year journey. It's not like wait 5 years before you see anything. We want to see parts of this in action. But to kick it off, I want to suggest that we have a networking grand challenge. essentially, build a self-driving network. The definition is, self-configure, self-discover, self-configure, self-monitor, this and that. Essentially, this is what the DARPA did for the self-driving car. They set a goal. They had a price. It was $1 million. So if you guys have money, that'll be nice. But we have to figure out how to do that. The result would be how to allow people to work at a higher level. Instead of sitting in the weeds and trying to figure out, I've got a Junos 16.1 here, I've got Junos 14.1 there, I've got iOS, if you know what iOS is, it's not the phone thing, but the other iOS. I've got SROS, I've got all these different things. Here's the CLI, they're all different. Can we work at a higher level? And if you can, now I can work on things like service design, or I can have a system, not just a box, but a network that's much more adaptive and anticipates service changes, and much safer too. So if I have a security breach, I can detect it much quicker and do whatever I need to mitigate that. So one possible challenge is, can I have a data center that runs by itself for 6 months with no human intervention? People talk about a lights-out data center where there's no humans in the data center. But that only means that they're far away and they're telnetting or SSHing and doing all the work, but they're doing it remotely. Yeah, but that's just, there's still a human involved. The question is, can it run itself? Can it do the day-to-day operations that it needs to do? And can that all be done with no human intervention? And if you did that, what would the impact be? And what would the possibilities be? So what I want to challenge you guys is, first, we have to make this happen, and I need your help. But more than that, think about what the impact would be. When you think about the impact of self-driving cars, there's actually an insurance company in the US that says your premiums, if you own a Tesla and you run in the autopilot mode, for most of your driving, your premiums will be half of what they are today. So they have a lot of faith in the Tesla autopilot system. This is not a joke. This is actually the case. Go do your Google search. You have to live in the US, I think. But so people are saying there's a huge impact on how you think about insurance, how you think about accidents, how you think about ethics. Am I in the way? So in the case of self-driving networks, there's a big change in skill set. So you have all these people who say, I've got a JNCIE. By the way, it's really hard, and I can't get one. I tried. But, or you have a CCIE. Fine. It's all good. But you need to think now at a higher level. So you move from being a network geek, and I understand OSPF, I don't know what that is, or this other thing called ISIS, which I know what that is. And I know how to change the metrics to do different things in the network, or I know BGP policies, to know how to design a new service. I know how to put services together to have a more compelling service for my customers. Or turn your network know-how into, I can tweak these algorithms. Because at the end of the day, you have this machine learning thing at the background, and you have to change it. You have to tweak it so that it's more effective. So your skill set really changes. And GM is looking at this and saying, okay, we have all these people who know how to drive cars, but we need more people who do programming. There's seats up here if you want. So there's this big change, there's a big impact in how you think about the job. There's another aspect that the network gets out of the way. There's a famous blog 5 or 7 years ago about the network is in my way. So I'm trying to do all this, and the network gets in the way. And if the network is truly monitoring things and adapting in real time, changing itself, then the network gets out of the way. And maybe the most important part is security becomes automated. Really, not just automated, but it becomes the good guy bot versus the bad guy bot. Today, what we have is a situation where people are coming into the network with these really smart algorithms, with these huge botnets, and turning a video camera into a DNS attack system. And we're sitting there trying to fight this with humans. I mean, sorry, you're going to lose. So can we actually turn the computers around so that we defend against an attack from a bad guy botnet with a good guy botnet? So, okay, this is a US-centric example. Sorry, I should give you something with FIFA, but take it as it is. Imagine that in 10 years, you have a big event. So it could be a sporting event, could be a concert, could be whatever. And instead of planning that, oh, I have this event coming up 2 years in advance, 5 years in advance. By the way, the Japanese started planning for the 2020 Olympics in 2015. So 5 years in advance. You just say, oh, the event is tomorrow. And you just call up a bunch of self-driving trucks to take this equipment, dump it on the field, or dump it in the stadium, or dump it in the concert hall. And then it self-organizes, says, oh, there are lots of people here that are tweeting away. I need more bandwidth here. And all these things move around, find it where they need to be. The network forms itself. The network does its thing. And then after it's all over, all this equipment is taken away to the next concert or next event. Yeah, it sounds crazy. That's where all these things start. But I think this can be done. But again, like I said, you guys think about the impact, think about the possibilities. So I think this is a compelling vision. I think there's really some legs here. And I think there's some imperatives coming out of this. There's the economic imperative. People say that running the network costs too much. And if you look at it, the biggest part of the cost is actually OpEx. So rather than, coming and beating us up, beating up us poor vendors and saying, make your equipment cheaper, which we do, by the way, year over year, attack the really hard part, which is operations. There's an efficiency imperative. The resources that you actually have, can you use them better? Can you spin up resources as you need it? So the promise of virtual networking, virtual VNFs, virtual network functions, is that I can spin up a resource and spin it down or change it as I need to. But we don't have an infrastructure that can really use that. So can we spin up resources as we need it? Can we change it around? And when I do have a resource deployed, can I use it effectively? There's an agility imperative as well. Can I bring up new services much more quickly than I do today? Can I, having the service in play, can I predict, anticipate, and adapt the service in real time? Because, of course, the networks change, the customer's need changes, bandwidths change. And of course, like I said, the security imperative, can I quickly diagnose, isolate, and either remove or mitigate an attack? And how quickly I can do that is actually really important. And can I do all this with no human intervention? So I think this is a vision worth pursuing. I think maybe one way to get there is this networking grand challenge. But however we get there, we need to think about building a self-driving network. We need to think about what the impact of that will be on how we design our NOCs and how we run our NOCs. We need to think about what the impact will be on what we can offer as services and how quickly we can do that. And finally, we need to think what we could do if we had one of these. Because it's not just, oh, my network today, as I build it, will get cheaper, which it will, but what new things can I do that I did not anticipate? So, yeah, that's it.